This video gives you some notion of what it takes to replace the wheels and axle on a rail car. We can easily imagine coming up with a model of the axle and the wheels, and we can separate the axle from the wheels and take a look at how we expect that axle to be loaded when the train is in service. I added some extra step on this particular shaft that may not be there in the train shaft, but the important thing is that we have the bearings on the outside here and there that we will have load pushing down on those. The wheels will be on this shoulder, and the load will be pushing up there of equal and opposite magnitude to that exerted by the bearings. And that exposes the center section of the shaft to a pure bending moment. The other thing to keep in mind is that the shaft rotates, and because the shaft rotates, the stress in the shaft will vary from the bottom to the top of the shaft. In this case, because of the way I applied the loads, I have a tensile stress on this side, and as the shaft rotates, we would move around to a compressive stress on the top side. Any materials element from the bottom where we have tensile stress, it passes through zero as you move around as the shaft is rotating to a compressive stress, back through zero and back down to a tensile stress again. So this is a pretty straightforward cyclic variation in the stress that is brought about by pure bending of a rotating member. The railroad axle that we just discussed is experiencing what's called fully reversed cyclic loading, where the maximum stress is equal in magnitude to the minimum stress. We go from tension to compression in that rotating shaft that is subjected to pure bending loads. If we control those loads so that they are well below the yield strength of the material, we can still get failure. The failure occurs after many stress cycles. It is by sudden ultimate fracture, and there's essentially no visible warning in advance of that failure. If we were to look at a failed component, we would note some very characteristic features on that component. The first thing to notice is these interesting marks, these lines, which have a radius of curvature that point back to the initiation site of the fatigue failure. So what happens is you cyclically load something, and the vast majority of the cycles are taken up in initiating a sharp crack. Then those cracks grow according to linear elastic fracture mechanics, and with each cycle you get a slight growth of the crack length, which leaves this characteristic beach marking line. Eventually those cracks get so large that the remaining intact ligament cannot handle the applied load, and you get fast fracture. Now we're ready to start characterizing how we're going to manage predicting the number of cycles required to cause fatigue fracture. So if we go back to the shaft that we actually did our finite element analysis on, it's going to look something like this. We have the wheel loads on the axle. We have the bearing loads equal and opposite on the axle, so that between these loads we have pure bending. And under those circumstances, we're going to get a shaft that wants to bend like so, which is going to put the upper surface in tension and the lower surface in compression. As the shaft rotates, every materials element moves from tension to compression. And so if we were to plot the stress as a function of cycles and a materials element on the outermost boundary, remember, we're going to concern ourselves with the outermost boundary because that bending stress is going to be our moment times half of our diameter over EI, right? So it's a pretty straightforward calculation. And what we find is that if we start at zero stress, if we're right at the neutral axis, and then we rotate, we find we get a cyclic sinusoid. That's a pretty ugly one, but we get a cyclic sinusoid. And this is one cycle. It makes sense to ask the question, how many cycles until failure? We want to be able to guarantee a lifetime for our component. So we really need to know how many cycles will cause failure. This initial fatigue problem was looked at by a gentleman named August Wohler, who first thoroughly studied it, and he was looking precisely at the same example I was showing you, and that is axle fatigue in trains. So we have to characterize that cyclic loading, which means we need to know the stress amplitude, the mean stress, and the number of cycles to failure. So if you were to look at that cyclic load, in this case it's pretty simple because our mean stress is going to be equal to 0. And how do we find that mean stress in general? It's 1/2 the maximum plus the minimum stress. The other thing that we need to find is the stress amplitude. The stress amplitude is going to be half the difference between the max and minimum stress. This up here is the max stress. This down here is the minimum stress. And this kind of loading is called fully reversed loading. That is when the mean stress is equal to 0. And all of the fatigue data that we use in determining lifetimes of components is experimentally collected using fully reversed loading. So everything that we originally knew about fatigue, which really came from Wohler's original studies on train axles, is for mean stresses equal to 0. And what Wohler found is that if you vary the stress amplitude and measure the number of cycles to failure, so this axis becomes NF and the y-axis is the stress amplitude, Wohler found that this obeyed a power law relationship. And this power law relationship was later described by Baskin and takes on a form that is attributed to Baskin called Baskin's law, where sigma A, and now we put a little R on that, which means stress amplitude for fully reversed loading is going to be equal to some coefficient times the number of cycles to failure raised to the power B. So B is going to be negative because this is a negative power law relationship. As the stress amplitude goes up, the number of cycles to failure goes down. So there was a lot of data that supported this for fully reversed loading. So let's go ahead and fix this and make sure we're saying sigma AR. And this is a very important foundational relationship between stress amplitude for fully reversed loading and the number of cycles to failure. And we're going to go through all sorts of mental gymnastics to convert a more general loading into a fully reversed loading so that we can then use all of the stress life data that is collected for all sorts of materials out there. Now, there's a very important thing when we look at these SN curves. So we're going to call these things, these are SN curves, otherwise referred to as stress life curves. And there is something important here, and that is we always ask ourselves, is there a stress amplitude below which we have infinite life? So that stress amplitude is something that we call the endurance limit, SE. SE is the stress amplitude below which we have infinite life, and it is given the name the endurance limit. As you can imagine, finding the endurance limit is a pretty important thing, and the endurance limit is going to depend upon the material, the fabrication process, and the loading. So again, we're going to have to do lots and lots of things to sort out how to find endurance limits for a particular component that is exposed to fluctuating loads. The other thing that we're going to have to sort out is how do we adjust Baskin's law for mean stresses not equal to 0? That becomes an important question. So let's go back to this Baskin's law briefly, where we plot the fully reversed stress amplitude against the number of cycles to failure. And something strange sort of happens, and that is down here below 10 to the third cycles, this no longer follows this simple power law. It switches to a different kind of power law. And the other thing we talk about is the endurance asymptote is often associated with 10 to the 6th cycles to failure. Usually what we do is we plot Baskin's law as log sigma AR is going to be equal to log A plus B log NF. And so what we do if we plot it logarithmically, the log of the number of cycles to failure and the log of the stress amplitude, we find some straight line regimes. Look, if we have no cycles to failure, then our stress amplitude is equal to our ultimate. And then we have a drop off at 10 to the third cycles. We then get a change in slope. and at 10 to the 6th cycles, we may or may not get an endurance limit. And it is this regime in here between 10 to the 3rd and 10 to the 6th cycles that we call the high cycle fatigue, HCF. From 0 to 10 to the 3rd, that is called the low cycle fatigue regime, LCF, and this beyond 10 to the 6th is the infinite life regime. Our task for any given combination of material and loading is to figure out first, so are we in the infinite life regime? If not, are we in the high cycle fatigue regime? If we are in the high cycle fatigue regime, how many cycles can this particular component endure? And then if we're in the low cycle fatigue regime, well, we're in trouble because our part isn't going to last very long. These are the sorts of issues that will take up the remainder of this class.